Have you ever looked at a string of events and just wondered, what are the odds? Is that just a wild coincidence or is something else going on? Well, today we're going to crack open one of the coolest tools in statistics to figure that out. It's called the binomial probability distribution. And trust me, it's the secret key to understanding chance in all sorts of situations, from something like a simple survey all the way to the high-stakes world of professional sports.
And speaking of sports, we are going to put this tool to the ultimate test by digging into a classic debate. I mean, if you're a football fan, you've heard this one a million times. The overtime coin toss. Is it really just a 50-50 shot in the dark? Or does winning that toss give a team a real, measurable leg up? That is the mystery we are here to solve today.
So here's how we're going to do it. First, we'll dive into the overtime mystery itself. Then, we'll get our hands on the tool for the job, the binomial checklist. After that, we'll decode the language of probability, run a quick practice round, and then we'll deliver the final verdict on that coin toss.
Okay, let's get right to it. Section 1, the overtime mystery. Before we can answer anything, we need to know what we're working with. We need to look at the cold, hard data. What actually happened in all those games over the years?
And here are the numbers. Now, what's really important here is that this isn't some small sample size. We're talking about a massive data set, 460 overtime games. And in those games, the team that won the coin toss went on to win the whole thing 252 times. Now, right off the bat, you can see that's more than half. But the big question is it enough more to matter, or could that just be a random fluke?
To figure that out, we need a very specific tool, and that tool is the binomial probability distribution. But, and this is a big but, we can't just use it on anything. We have to make sure our problem, the NFL coin toss data, actually fits the criteria. So think of this next part as our investigator's checklist.
Okay, here it is. 4 simple questions. 1. Is there a fixed number of trials? Yep, 460 games. Check. 2. Are the trials independent? You bet. The result of one coin toss has 0 effect on the next one. Check. 3. Does each trial have only 2 outcomes? Absolutely. The team that wins the toss either wins the game, a success, or they don't, a failure. Check. And 4. Is the probability of success the same for each trial? Well, for this, we're going to start with an assumption. We'll assume it's a fair 50-50 chance, or 0.5, and then we'll test that assumption. So, check. Our situation fits perfectly.
So now that we know the binomial distribution is the right tool, we gotta learn its language. It's actually pretty simple, just a few key variables that represent all the pieces of our puzzle.
First up, you've got n. This is just the total number of times you run the experiment. So for us, it's the total number of overtime games we're analyzing. That makes n equal to 460. Easy enough.
Next, there's x. This is the specific number of successes that we actually saw happen. In our case, a success is when the team that won the toss also won the game. So our x is 252.
Then we've got p. This is the probability of success in any single trial. Remember our assumption? We're starting from the idea that the coin toss is pure chance and gives no advantage. So under that assumption, the probability p that the coin toss winner also wins the game should be 50%, or 0.5.
And last but not least, there's q, which is just the probability of failure. This one is super easy. It's always just 1 minus p. So if p is 0.5, then q is also 0.5. And that's it. We've got all our variables ready to go.
All right, before we tackle the big NFL question, let's do a quick warm-up lap. We'll run through a different example just to see exactly how this whole process works in action.
So let's check out this case. Imagine a survey finds that about 5% of adults don't carry any cash. Okay, so if we just randomly select 10 adults, what is the probability that exactly 2 of them are cashless? Well, this totally fits our checklist, right? And we can easily spot the variables. N is 10, our sample size. X is 2, the number of successes we're looking for. P is 0.05, and Q, which is 1 minus P, is 0.95.
Now you could grab a calculator and plug all of those numbers into this beast, the official binomial probability formula. I mean, look at it. It's got factorials, exponents. It's a whole thing. And yeah, it works perfectly, but man, it is tedious and it's so easy to make a tiny mistake.
But here's the great news. We don't have to do that. In the real world, nobody does this by hand anymore. We use software. A program like StatDisk, for example, lets you just pop in your n and p values, and bam! It instantly calculates the probability for every single possible outcome. And that is exactly how we're going to solve our NFL mystery. All right, this is it, the main event. We've got the data, we've got the tool, and we know how to use it. It is time for the final verdict. Let's find out what the numbers really have to say about that NFL overtime coin toss. So let's start with a picture. If winning the coin toss were pure random chance, that 0.5 probability we talked about, then out of 460 games, we would expect the winner to win 230 times. That's our baseline. But what we actually saw was 252 wins. You can see the difference right there. The million-dollar question is that gap big enough to mean something?
And this puts the question perfectly. We need a solid mathematical way to decide if 252 is just a normal random fluctuation around that 230 number, or if it's so far out there that it's really unlikely to have happened by chance alone. In other words, we need to test for statistical significance.
And here's a really handy way to do that, the range rule of thumb. It basically draws a line in the sand for us. It says that any result falling more than 2 standard deviations away from the average is considered significant. Anything inside that 2 standard deviation window is just considered normal, random noise.
So let's run the numbers for our NFL data. We already know the mean, or the expected value, is 230. A quick calculation shows that the standard deviation, which just measures the typical spread of the data, is about 10.7 wins. Using our rule, we find our significantly high threshold. You take the mean, 230, and add 2 standard deviations. That gives us 251.4. That is our line in the sand.
And remember, the actual number of wins that we saw was 252.
And there you have it. That's our verdict. Because 252 is greater than our threshold of 251.4, it falls outside the range of what we'd expect from random chance. The result is officially, statistically, significantly high. This was not just a lucky streak.
And if you want the smoking gun, look no further. We can go back to our software and find the exact probability of getting 252 times or more wins just by sheer luck. And that probability is a measly 0.0224. That's only about a 2.2% chance. In statistics, a general rule of thumb is that anything less than 5% is significant. This clinches it. The data strongly suggests there was a real tangible advantage to winning that coin toss.
So there we go. We used the binomial distribution to crack the code on a long-standing NFL debate. And this way of thinking, this tool, is something you can now use anywhere you see a series of yes or no outcomes. So the next time you see some crazy statistic or a so-called lucky streak, you have the tool to look a little deeper and ask the real question: is it really just chance?